you are transmitting this colloquium, Daniel? Yes? So you... Okay, we can start now? Okay. Okay, I will speak a little bit Spanish, okay. Muy buenas tardes a todos. Bienvenidos nuevamente al coloquio del Instituto de Física. Aquellas personas que no quieran aparecer en la transmisión, por favor, apaguen sus cámaras. Y después de este anuncio, pues no me queda de otra más que darle la bienvenida, una calurosa bienvenida a la profesora Lucia Reining. Y para presentarla, bueno, voy a hablar un poco en inglés para que ella nos entienda. Let me introduce Professor Lucia Reining. She's an exceptional great senior researcher of the French Centre National de la Recherche, Scientifique, no? Working at the Ecole Polytechnique in Palazzo, France. After his master's degree at the University of Aachen in Germany, she moved to Tor Vergata University in Rome in order to work with Rodolfo del Sole on a tie binding model for semiconductor surfaces. Let me tell you that I arrived some years later, a few years later, and Lucia was a rock star in Rome, and Rodolfo just talked about Lucia, so it was very hard to me to be there. Okay. So she remained for a PhD about many-body perturbation theory, calculated in tie binding, and at that time it was in the 90s, no, at the end of the 80s, at the beginning of the 90s, and she then decided to learn about first principle calculations and move to the Centre Européen de Calcul Atomique et Moléculaire, which was located at Orsay in France at that time. So she had a Marie Curie fellowship, allowed her to work on questions of theory and algorithms in the framework of many-body perturbation theory. And she got involved in European projects, which laid the foundation for long-lasting collaboration and friendships, and which culminated in the European Theoretical Spectroscopy Facility. Okay, of which she is the co-founder. At that time, she and her co-workers started their activity on the first principles solution of the Bethe-Salpeter equation for the description of excitons. She then entered to the CNRS, and today her work combines analytical and numerical approaches, including the development of density functional and green functionals, approximations, and applications, often in collaboration with the experimentalists. This is why they have the European Theoretical Spectroscopy Facility. Okay. Besides journal publication, a joint book with Richard Martin and David separately about interacting electrons reflects her view on many electron physics, and her work has been recognized by a silver medal of the CNRS in 2003 election. And she was elected APS fellow in 2007. And an ERC, well, I don't know what is an ERC, but I guess European Research something, probably you can tell us, advanced grant in 2012, and the Genzer-Kastler Prize of the French and German Physical Societies in 2020. So I'm very happy because I met Lucia some years ago, a few years ago, just a few. And she's an extraordinary researcher, and she has done a lot of work in this topic about many-body. And the title is very compelling, no? The quantum many-body problem, unsolvable, but keeping us busy. So thank you again for being here, Lucia, and well, the screen is yours.
Thank you. Thank you very much, Cecilia. It's so nice that you invited me. I'm really happy to be virtually with you. And since I don't know you, I didn't know exactly what kind of things you would like to hear. So I will give you a little overview of what we are doing, why we are doing this, what is the problem, how we try to approach the problem. And I would suggest that if you want to ask questions, you interrupt me. No, I don't probably see if you are asking questions, but you can just interrupt me and I will be happy to discuss. And if the talk doesn't come to the very end and in every detail, that's not a problem. Okay, so what I will show you has been mostly done in the Palaiseau theoretical spectroscopy group and also with friends outside the group. And the most important people here, a group of PhD students and postdocs who were or are in the group: Ayub Awina, Vitali Gorelov, Arnaud Laurin, Martin Panholzer, Igor Reshetniak, Marco Vanzini, and Sky Zhu. And also my permanent colleagues, Matteo Gatti and Francesco Sottile. And we have collaborations with theorists in the US mostly, and also a lot of collaboration with experimentalists. At the University of Magdeburg, you will see an example by Martin Feneberg and Rüdiger Goldhahn, and then mostly with synchrotrons, Soleil, which is also in Paris, and the Swiss Light Source. So our group is called Theoretical Spectroscopy Group, and this means that we are trying to describe, understand, predict phenomena that have to do with spectroscopy, spectroscopic properties, in particular electronic excitations. So this can be things like photovoltaics, and I put some pictures here, optical data storage, the color of materials, photosynthesis, all these kind of things. And we want to look into this using theory. So this is this little magnifying glass here. And this is a quantum many-body problem because we look at this on the quantum level, and these are electrons and nuclei. And of course, it's a many-body problem because we're talking about real materials which have 10 to the 23 particles. So what is the quantum many-body problem? This will be my first point. And I will then tell you our particular way to approach it, which is using and developing functionals. And I will in particular come to many-body perturbation theory and show you a few examples. And then if I have time, I will also show you recent work more in the framework of density functional theory, but not only. And it's a new approach that we call the connector approach, and which we want to be something that we would call ecological. So the quantum many-body problem. You know, we say we are theorists, but in principle, we are not theorists because we do not find new fundamental interactions. We do not find new elementary particles. We have an equation, which is the Schrödinger equation, which is supposed to be known. And the only job that we have is to solve it. Now, this Schrödinger equation is written here. It's a many-body Schrödinger equation because we have many electrons, for example. So we have the Hamilton operator that tells you what's going on. And then we have the wave function. And the wave function depends on the coordinates, space and spin coordinates of every particle. So you could say, but that's boring. So we put this in the computer and we solve it. Of course not. This problem is not, at least not exactly solvable, unless you have like 2 or 3 electrons and you can do some numerics. And this is because, of course, the full solution depends on the space and spin coordinates of every electron. So we have 3 times n coordinates. And then this is an exponential problem because everyone talks to everyone. And so you have to form all kind of couples. So this is just not solvable. And also, if you could solve this problem, you would have a wave function that is so huge that you cannot store it. So this is the quantum many-body problem. And of course, we would solve it, and we would solve it because there are a lot of, we would like to solve it because there are a lot of interesting things. And already in the name, you can see the many facets of it. So the first part is quantum. What does it mean, quantum? It means that we cannot exactly know where an electron is. For example, electrons are not in a position, they are in states. And this means that we have quantum fluctuations. For example, if you have two spherical atoms that I depicted here, then over time, you will have little dipoles that are forming. The atoms alone, if this was not the case, they would just ignore each other. But because there's little quantum fluctuations, you have a dipole on one atom. This induces a dipole on the other atom, and now you have dipole-dipole interaction, and you have an attractive force. And this is called the van der Waals dispersion interaction. And this is very important because, of course, you might think that you might two spheres, you don't care. But in reality, even though this is a weak force, it's very important. And the example I have here is the alanine helix structure of alanine polypeptides. So we are talking about structure of proteins. And this is not my own work. It has been given to me by Mariana Rossi, so it's published in this article. It's a nice example because they did simulations of how this helix evolves over time. And this helix is stable in experiment up to more than 700 Kelvin. But if you ignore this weak interaction due to quantum fluctuations, and this is here the picture on the bottom right, then the helix, if you heat it up, after 30 picoseconds is already gone. The structure is destroyed. But if you take this weak interaction into account, then the helix remains stable as it is in experiment. And of course, you know that everything that's linked to protein structure is extremely important. The next ingredient is many body. Let's say more than one body. And this is already a very important problem. Of course, in classical physics, you can have two pendula, for example. If you have just one pendulum, well, you have this oscillatory motion that you know very well. But now if you couple the two pendula, then you will have a motion here of the blue and the red. So the blue pendulum and the red pendulum that is coupled, and that is not longer a simple oscillation, but you have beats. And you can have a situation where one pendulum is moving very fast and the other one very strongly, and the other one is almost standstill, and vice versa. So the coupling of bodies completely changes their behavior. And when we say many body, we're actually talking about many, many, many bodies. As I said, it can be of the order of 10 to the 23 when we go to condensed matter. And then you have still new problems. And one very important one is the following. Suppose you have a potential that's completely flat. So a background potential, and then you have electrons. And this is called the homogeneous electron gas. And the density that you would write down on paper of these electrons in this completely flat background is a homogeneous density, because that's the symmetry of the Hamiltonian. So on paper, the homogeneous electron gas is actually homogeneous. But if you go to low density, then the electrons eventually, you will find another picture. And this picture that I show you here has been calculated by David Sepperley using quantum Monte Carlo. And it's a picture that I took from the book Cecilia was mentioning earlier. And this is actually a two-dimensional electron gas. And you see a sort of crystal. So the electrons form a crystal, and this is called a Wigner crystal. And this is because when you have all these electrons in interaction and they talk to each other, they decide that they would arrange in a regular pattern. This is the crystal. So this is something that happens in the computer, because actually in the computer, life is never perfect. So you have boundary conditions, you have initial conditions, this do a little symmetry breaking. And as soon as you have the smallest symmetry breaking, these electrons fix themselves somehow. If you would do the simulation with another initial condition, you would get another crystal, but it would be the same crystal, but maybe oriented differently, shifted differently, but you would again have the same correlation between the electrons in the same kind of ordering. So that's something that happens when you have these many, many, many electrons. And of course, it's very difficult to predict what would here happen exactly. Actually, even the crystals we talk about, usually the crystals made of atoms, is such a correlation effect, because the crystal, if you throw your atoms in empty space, they somehow decide that they stay in one place and they form this regular pattern. So they just talk to each other and decide how they want to crystallize. This is a pure many-body effect. So we have all these wonderful, super important, and actually very surprising effects of quantum many-body physics. And our job, as I said, is not to find a new Schrödinger equation. Our job is to rewrite and approximate this equation. Rewrite it in a way that is suitable for approximations. And we approximate it in a way that allows us to find answers to certain questions. It's very important to stress that we never ask all possible questions in the world. And this means that we actually probably don't need all the details of this wave function. We only have certain questions, and we try to get as good as possible answers to the questions that we have. And to do this, we, in Palaiseau and many others in the community, use functionals. It's not the only way to do. I have already mentioned quantum Monte Carlo, so you can also work with wave functions and do approximations on the wave functions. Our way to do is functionals, and this is what I will now introduce. So when you work with wave functions, what you do is you calculate expectation values, because what you're interested in is not the wave function, it's an observable. And the observable, which I called O here, is an expectation value of the operator that corresponds to the observable taken with the many-body wave function. This is a well-known expression. It's simply an integral. And the only problem is it's a huge integral, and so we cannot use it, but it's in a principle known expression. And we say that the observable is a functional of the many-body wave function because it's expressed in terms of the many-body wave function. Now, since this is so difficult, and since we cannot calculate and we cannot store the many-body wave function, and therefore we cannot calculate these integrals, the idea is to say, well, but maybe we don't need all this knowledge of the many-body wave function. Maybe there is something else that would also describe our system sufficiently well, or at least describe our observable sufficiently well. Let's call this object Q. So we would say the observable actually depends on Q. And of course, we would hope that this Q is an object that is simpler than the full many-body wave function. Q could, for example, be an observable itself. It could be the potential of all the atoms, for example. If it's an observable itself, sometimes it's also difficult to calculate. So we have a double problem. First, we have to know this Q, and then once we have Q, we have to know in which way the observable depends on Q. So what is the functional of Q? This sounds maybe a little abstract to you. So let's be precise. Many of you know density functional theory. In density functional theory, we say that actually the density fully describes our system. To be precise, the ground state electronic density describes fully our electronic system. This is our descriptor. So you see, this density is an object that is much, much simpler than the full many-body wave function because it depends only on one coordinate. But we do not know the density a priori. And so this is the problem. We do not know this Q, which in this case is the density. So the first problem to solve, if you want to go this way, is to find a way to get the density without calculating, again, the full many-body wave function, of course. And the clever idea of Cohn and Sham was to say, we can get the density from a reduced problem, an auxiliary world, a simplified world, a world without interaction, but with a modified potential. We call this an auxiliary potential. So a potential that is tuned such that in this simpler world where no interaction exists, we get the same density as in the real world. And this potential contains the external potential and the classical electrostatic potential, but it also contains this exchange correlation part, VXC, which is the Cohn-Sham exchange correlation potential. Now, the problem, which was the solution of the full many-body wave function, has been reduced to the solution of one electron Schrödinger equations. One electron, meaning that you have only one coordinate, and from these wave functions, much simpler wave functions, you can then calculate the density. And then you get objects like the Wigner crystal I have shown you before, but you have to know this exchange correlation potential. This is a little bit like building simulation chambers. So in physics, even if you are not doing theory, but even if you're doing experiment, it's actually a general strategy. Now, suppose that you want to know how your material behaves in zero gravity. Then you can do two things. Either you have a space shuttle, you fly out wide out in the space, and you look for a place without gravity, and then you measure your material. This is very costly, but it gives you the answer to your question, and it also gives you the answer to other questions like, is there a little green woman living out in the space? But that's maybe too much because you're not interested in this little green woman. So you can build a simulation chamber on Earth that creates zero gravity, that gives you the answer to the question whether your material, how your material behaves in zero gravity, but it will not answer, of course, the other question you're not interested in anyway about the little green woman. So this is a simulation chamber. This is an auxiliary system. And the same thing is the Kohn-Sham system is made to give you the density and nothing else. Okay, so now suppose you have the density from this Kohn-Sham system. The next problem is that now you have the density, you have to express your observables, O, in terms of the density. So in general Q, here in particular the density. And this is, of course, also a very tough problem. In the density functional world, mostly people try to approximate the total energy in terms of the density. This is the preferred observable in the density functional world. Other observables, the one we are interested in very often, namely spectral functions, are extremely hard to approximate in terms of the density, so we don't even try. Okay, but this general problem have a descriptor that you have to determine, and from this descriptor get observables is what is at the basis of every functional approach. So it is also at the basis of what we do with Green's function. Because when you use Green's function, you have a completely equivalent strategy. You have, instead of the density, the descriptor of your system is a one-body Green's function. You see? It's a little more complicated. It is non-local in space. There's two space coordinates, and moreover, it depends on frequency. It's a sort of generalization of the density to a density matrix, which would be non-local in space, but then also an object that is non-local in time. It depends on a time difference and therefore on frequency. And exactly as in the case of Kohn-Sham, you can build an auxiliary system from which you get this a priori unknown one-body Green's function. And this auxiliary system also has an exchange correlation potential-like object that you do not know, and this is called the electron self-energy. And because the object you are looking for is more complicated than the density, also the potential is more complicated than the Kohn-Sham one. It's again non-local and frequency dependent, and it's a functional of the one-body Green's function itself. So more complicated object, more complicated auxiliary system. But we gain, because when we know the one-body Green's function, we can construct more observables easily. We know the exact expression for the total energy, contrary to density functional theory, where we do not know the exact expression. Here we know it, it's the Galitzky-Migdal expression. We know the exact expression for a spectral function, A. It's just the imaginary part of the one-body Green's function. We know the exact expression for the density and many more things. Other observables are still not accessible in an easy way. For example, we do not know the exact expression of the dielectric function as a functional of the one-body Green's function. There, we still have to do approximations. And we can go on. There are other functional theories, like dynamical mean field theory, if you're interested about it, in that we can talk about it at the end. In dynamical mean field theory, your object, your descriptor is a local Green's function, a site local Green's function, and your auxiliary potential is a site local self-energy, and then you can construct site local spectral functions, but not a total energy, for example. And this can be generalized, and if you're interested in generalizations, you can look at these papers of ours. The important thing here is that actually none of these auxiliary potentials that we need to get our fundamental descriptor, none of these auxiliary potentials is actually known. And therefore, we have to do approximations to get them. And one very prominent approximation that we use when we work with Green's functions is perturbation theory, and in particular, many-body perturbation theory. So let's come to the many-body perturbation theory. So our target is the one-body Green's function. Again, it depends on 2 space points and 2 time points. I've written this here. I put an X because it also actually depends on 2 spin coordinates. And the one-body Green's function is actually a propagation. So it describes you what happens if you insert an electron in some place at some time, and you monitor the propagation, the probability to find it at another place at another time in this many-body system. So N is the many-body, N-body ground state, and the psi and psi dagger here are field operators for electron removal and insertion. And this is something that you can then expand, because now we are talking about particles that are moving in the system, and that is something very intuitive. And so both mathematically and with intuition, you can write down approximations. And we do this graphically with Feynman diagrams, because just the equations are very complex, but it's just a way to represent equations. And you can imagine what happens. So you have the propagation, we said, of 1 electron in a many-body system. And we describe this propagation by an arrow, this black arrow here. And what can happen? Well, the electron propagates, and then it sees the other electrons, the density of the other electrons. The density is this circle, and the way it sees it is via the Coulomb interaction, which is this dashed line. This is the Hartree term, the classical electrostatic interaction with all the other electrons. And this, of course, modifies the propagation. The second term is the fact that electrons are fermions. You cannot distinguish them, and therefore you can exchange Green's function lines here. And then you get the exchange diagram, which is actually the Fock contribution. So this plus this is Hartree-Fock. And then comes the interesting part. So you propagate in the system, you have a Coulomb interaction with the other electrons. The other electrons are not happy. Coulomb interaction is repulsive, so they would move away. So while you come, you are the electron, you come, you have a Coulomb interaction, an electron is moving away. This creates an electron-hole pair, a hole where the electron was before, an electron where it's going. This is a dipole. It makes a new potential with a Coulomb interaction, which again modifies the propagation. So this is a polarization diagram that modifies the propagation, and so on and so on. And so you can see that this is many-body perturbation theory in terms of the Coulomb interaction, because, of course, while we create all these new pairs and interactions, we get terms that are of higher and higher order in the interaction. And it's a sort of story writing. It's a story writing of what happens in this many-body system. And we sum all this up. And when we sum all these possible processes up, this is what gives you the self-energy, which is this auxiliary potential we are looking for. And the way the auxiliary potential acts can be phrased in terms of what we call a Dyson equation. So the propagation of the particle in the interacting system, which is called Green's function, G, is the propagation in the non-interacting system, plus a correction, which is due to all these possible processes. Now we have to make a choice, because infinitely many things can happen. And here comes the approximation. And we have to think of what is physically most important in the systems we're interested in. Certainly the classical electrostatics, the Hartree, certainly the Fock diagram, electrons are fermions. And since we are mostly working in large systems, in solids, in crystals, in liquids, it's the polarization, the screening. This is screening. So this kind of polarization diagrams are summed up to infinite order. And if you do this, you get what is called the GW approximation, which has been introduced by Lassedin already in the 60s. So the GW approximation is an approximation where the self-energy is built with the propagation of the electron, the Green's function G, and W, which is the screened Coulomb interaction, screened by the creation of all these electron-hole pairs while the electron propagates. And this screening is expressed by the inverse dielectric function epsilon to the -1, which is frequency dependent, and therefore the self-energy is frequency dependent. And V is the bare Coulomb interaction. So you see, this is very similar to Hartree-Fock. In Hartree-Fock, the self-energy is just the bare Coulomb interaction and the density matrix. Here we have the screen Coulomb interaction and the one-body Green's function. Very analogous. So Hartree-Fock, you can say that the electron in a Hartree-Fock system, it moves like an ice skater on ice. So the ice is frozen, it doesn't react, there's no polarization, the electron moves in the system. Whereas in GW, it's more like a boat on the water because the system reacts to the propagation, and in this way, it modifies the propagation. In fact, Hedin also called this object that then comes here, so the boat plus the water, the electronic polaron, because it's like the screening by the lattice. Okay, GW, most of you have certainly heard about it. It's actually today the gold standard to calculate band structures. I have already told you that if you have the one-body Green's function, you can easily get the spectral function, and this is how you get a band structure. You're probably also aware of the fact that when you try to do this in density functional theory, so you use the Kohn-Sham band structure, for example, in the LDA, then you usually get problems. In particular, the band gap is too small. This is an example of Michael Rolfing and co-workers, and this is just a germanium, very simple. So on the left side, you have the Kohn-Sham electronic structure of germanium. The Fermi level is at 0. You can see that this is a metal, but germanium in reality is a semiconductor. In fact, you should not use the Kohn-Sham band structure. We have seen the Kohn-Sham system is made to get the density, not other observables. So asking for the band structure is like asking for the little green woman when you have a simulation chamber for zero gravity. You shouldn't do that. In Hartree-Fock, you have Kopman's theorem, so you can ask for a band structure, but because your system is rigid, it does not relax, it does not minimize energies, the band gap is much too large. In the middle, you have GW, which is like screened Hartree-Fock, and then you have a reasonable band gap for germanium, and you are with your lines, which are the calculations, on top of the dots and filled and empty dots, which is experiment. So very good result for band structures. Again, very striking differences on the band gap. So that's gold standard. And you can get more out of your GW Green's function. So the spectral function is the imaginary part of the Green's function. The imaginary part of the Green's function is calculated from the imaginary part of from the real and imaginary part of the non-interacting Green's function and the self-energy, and you can transform the Dyson equation into this form. And then you will see that this spectral function has peaks where you have zeros in the real part in the denominator. This, of course, gives you a peak. This is what we call a quasi-particle. And also peaks where the imaginary part of the self-energy has structure, and this structure comes from the imaginary part of your screen Coulomb interaction. So excitations that are in the inverse dielectric function, like plasmons. And these create satellites. So you can see this on the left side, you have a non-interacting spectral function as a function of momentum, K. You have just single peaks because in a non-interacting picture, every electron is sitting on its energy level. And when you do photoemission, you remove an electron, and then you just see these energies. Whereas when you really do the spectral function calculation, you have an interacting system, you get broadening of the peaks, and you get these additional structures that are satellites. And this is the kind of calculations we frequently do. And we do this also to explain experiment. This is actually a very simple example here. Bulk aluminum and this is the experiment. So on the horizontal axis, you have momentum is in the Brillouin zone. This is the gamma point in the middle and the L points. And on the vertical axis, you have energy, and then you have the color code for intensity. So this is angle-resolved photoemission that is depicted here. Photon in, electron out. You measure its kinetic energy, and from this, you make conclusions on this energy electron removal process. Okay, so the Fermi level is on the top, and close to the Fermi level, we measure the occupied bands of aluminum, and you can see they are very sharp bands. This is the quasi-particle part of your spectral function, very sharp bands. That's what people usually calculate and talk about, also the experimentalists. But then you have a lot of more stuff. You have a sort of replica of these bands down here, and another replica, if you look closely, down here. These are the satellites. And if you now do your GW calculation, you also get a very good band structure as always, here. And now this is actually a GW plus cumulant calculation. I will tell you this in a moment, but you see we get the replica of the valence band down here, and then a second replica like in the experiment. So this cumulant, I don't want to go into detail, but roughly speaking, you have the same physics. So you have the screen-Coulomb interaction, and you have the one-body Green's function, and simply this physics is treated in a let's say higher order way with respect to GW. So you get a little better results on these satellites. This is why I show you this spectrum. Okay, it's still not perfect compared to experiment. You see that you have a lot of intensity missing here, and also here you have a lot of non-dispersing intensity missing in particular. We can also get this from the calculation. And this is what is here labeled GW plus cumulant plus plus. So these effects that then give you a very good agreement with experiments. So on the right side is theory. These effects are effects that are not correlation effects. These are not many-body effects. This is a good example for the fact that between theory and experiment, there are a lot of things going on, and you should not always interpret this as fancy correlation effects. For example, you have extrinsic effects. What does it mean? It means that when you interpret your photo emission, you think that you have electron removal, and the electron is excited, and then it's gone, okay? And your system is left with a hole, missing electron in some excited state, and that gives you the spectral function. But in reality, when the electron is excited, it's not gone. The electron has to fly to the detector. And when it flies to the detector, it goes through matter and through the surface. And on this way, it can do a lot of scattering. And when it does the scattering, it excites the system. For example, it excites plasmon. And so it will reinforce these satellites. But also because it scatters, it loses the information about its direction. And this is why these things are actually non-dispersing. They are not angle resolved because the electron forgets what its momentum is. And another thing that is important is temperature. It's the fact that even at the 35 Kelvin, we have measured here at 35 Kelvin, but even at that temperature in aluminum, the movement of the atoms does contribute. And it's again something that it makes the crystal non-ideal, and it destroys momentum resolution. And so again, it adds non-dispersing intensity. So these are two examples of things that we have put here and that really, really very much improve agreement with experiment.
For example, Lucia, in the experiment, you have some asymmetries or anisotropic features, no? That I mean, for example, yes, that, for example, no, you can look that it's not equal, the left-handed and the right-handed side, and it has to do with the preparation of the experiment more than the...
Yes, this is also true. So we had a lot of work on this, actually, also to describe all this, because even when you present your experimental results, there are a lot of hypotheses, right?
Right.
Because you have like the work function and things. So you sort of extract the spectrum from your experiment from the raw data, but you have a lot of things that you have to know, to zeros to Z and angles to convert, and there are really many things, yeah. And so at the end, it's not perfect.
Yeah. Okay. Thanks.
And any other questions since we are just talking?
You can, pueden interrumpir o si quieren que interrumpa.
Yeah, you're really, really welcome to interrupt. Really.
Yeah. Okay, thanks.
I know it's lunchtime for you, so I think you are hungry, but still.
Yeah, well.
Okay, let me go on, but please feel free to interrupt. Okay, so this was about the one-body Green's function, but another experiment that we are very much interested in is absorption. And when you do absorption, so I have here again the same band structure of germanium, you do not kick out electrons as you do in photoemission, you excite electrons from a valence band to a conduction state. Okay, so the photon comes, you excite the electrons, this takes energy from your photon beam, and then you measure what comes out, the intensity is reduced. Okay. Now you can immediately see that when you do this, you can definitely not forget about this electron. It stays in the system. So now you have the hole in the valence band and the electron in the conduction band. And this makes a two-body problem. And therefore, strictly speaking, you have to work with two-body Green's functions. So how do we do this? You can imagine that when you do absorption, so you create your hole, but you still have an electron, which is like an extra electron, but somewhere else. The hole is dressed. Dressing means that the hole itself, it has all these processes we have been talking about. So, for example, screening, right? Let's say the hole is screened. The electron is also screened. So we know we have these two screened particles, which we can describe by two one-body Green's function, one for the hole, one for the electron. So the two together is our first approximation for the two-body Green's function or for the two-body correlation function, and we call this L0. But now we know this is not everything, because the hole is positive, the electron is negative, these two will interact, and this is what we call the electron-hole interaction. And the electron-hole interaction actually comes from the fact that when you excite your system, then you change the system, so you change its density if you describe in terms of the density, or you change its Green's function if you describe in terms of the Green's function. And this changes all these auxiliary potentials, right? For example, the Hartree potential depends on density. So if you excite, you change the density, you change the Hartree potential. And this change of potentials makes this effective interaction. And I have written this here. So from the Dyson equation of the one-body Green's function, we now move to the Dyson equation of for the two-body Green's function or correlation function, which is written here. So the L0 is just electron and hole all alone. Each of them is stressed, screened, okay? But then we have this additional interaction because the Hartree potential changes when we excite and the self-energy changes when we excite. And this equation is called the Bethe-Salpeter equation. And we have to approximate these auxiliary potentials. The Hartree potential we know, of course, exactly. And its change with excitation is just the bare Coulomb interaction. And the self-energy is something we don't know exactly, but since we have adopted earlier the GW approximation, we can calculate this derivative. So we derive GW with respect to G, and this just gives minus W. And so minus W is actually the screened electron-hole attraction. This is why it's minus. It's attractive because electron and hole have opposite sign. And this is how you get it. Okay, and there have, of course, many people have been working on this. Okay. Now, when you have this electron and this hole, and they are attractive, these make bound pairs that we call excitons. And excitons is something that you might know from textbooks. For example, you might know the Wannier exciton. So in a Wannier exciton, you have a hole and an electron, and they're interacting with a screened Coulomb interaction. And this makes bound states, for example, in the band gap, and the binding energy. So the difference between the energy of these states in the gap and the gap itself is called the binding energy. And this binding energy is inversely proportional to the square of the dielectric constant. Because the stronger screening is, the weaker is the screened electron-hole interaction, and so the smaller is the binding energy. This is absolutely textbook knowledge. But when it comes to real systems, of course, all this is very simplistic. And as an example, okay, we can look at this expectation that when you have a large binding energy, it means that screening is weak. And when screening is weak, then the electron and the hole, because the interaction is strong, should stay very close to each other, like in a Frankel exciton. So this is the work of Vitaly Gorilov, who is a postdoc in our group, and with all the people I have mentioned here. And this is actually work that was supported by the French electricity company, EDF, because everything that's linked to photovoltaics is very much linked to this optical absorption, and people are very interested in excitons. So this is why we have a strong link to photovoltaic applications. And the material here is V2O5, vanadium pentoxide. It's a layered bulk oxide. And you have on the right side in red the experimental absorption spectrum measured by our experimental colleagues Feneberg and Goldan, and in blue the calculation of Vitaly. And this is a typical, let's say, agreement that you get when you solve the Bethe-Salpeter equation for a reasonably complex material. We have the main peaks that are all there, and everything's nice. The little black arrow here is what we call a dark exciton. So it's an excitation that you cannot see in the optical spectrum, but that you get from your calculations. Okay, and to show you how important the electron-hole attraction is, you have here again in blue the calculated spectrum, but in orange you have the spectrum that you get if you do not include the electron-hole interaction. So you calculate, you do a GW calculation for the band structure. You have your electrons, you have your holes, but you don't let them interact. And then from this, you build the transition between these bands, and this gives you the orange result. And you see it's very, very much shifted to higher energies with respect to the true absorption spectrum calculated in Bethe-Salpeter. We have a binding energy, so a difference between the absorption onset and the photoemission gap, which is about 1 electron volt, a very strongly bound exciton, very strongly bound exciton. Okay, so you would think that, like in a Frankel exciton, the electron and the hole are very close to each other, and we can actually calculate where the electron goes if the hole goes somewhere. Okay, remember this is a correlated problem. You have an electron in the hole. It's a two-body problem, so you cannot say here is the hole, here is the electron. You can only say if the hole is here, where would the electron go? Okay. The most probable place for the hole is actually on a bridge oxygen here. It's a little blue dot. So we put it here and we look where the electron goes. For the exciton of this first peak, it's the first bright exciton. It's the first exciton that makes significant weight in your spectrum. And you see that actually the electron is distributed over a large radius, over many, many atoms. This is the plane here, okay? Over many, many atoms. So we have a strong binding energy, but it's not true that the electron is just sitting on top of the hole. It's actually very distributed. And this is something you can only get from this kind of ab initio calculations. We have supported the calculations by tight binding models, and we have also understood that this is due to the charge transfer nature of this excitation, but still ab initio calculations can really give you this kind of details. So we can understand excitons beyond textbook models. Then you would, of course, say, but what actually really happens in this material? What are these pictures about, right? And this is something that has been motivated, this question for us, by a very nice collaboration that we had with a museum. This is the Museum of National History in Paris. And this work has been supported by a Cultural Heritage Fund. And it was a project about photography. So the first black and white photography was actually 1839 by Daguerre. And you might know that this caused a lot of attention and everyone wanted to have photos. And it was really a sort of craziness in the population. But not even 10 years later came Edmond Becquerel with the first color photography, which was much less noticed. And the reason is that he found the process to make a color photography. This is Edmond Becquerel, and this is his cliché. But he didn't find the way to fix the colors. So you would shine light on your photographic plate, okay? It would get the colors of your light, but then if you did not put this thing in the dark, it would continue to change color. And this is, of course, completely useless for a photo. And moreover, it poses problem of how to conserve these things. So this is the rainbow photo, a rainbow photo by Edmond Becquerel, but it's in the dark drawer in a museum. And this makes it also very difficult to make experiments, and therefore they asked us whether we could, with calculations, help them to answer a few questions about this process. And this is how we came to ask ourselves what's in detail going on in the materials, and in particular we were interested in silver chloride, which is the main material here. Okay, so I will not tell you about answers of cultural heritage, but what this brought us to do, as often in research, you start to do something and then you find something else. Okay, so what's going on? What's going on in optical absorption? What's going on when we shine light or any other perturbation on a material? Well, we can do this in linear response. So we think that our perturbation is weak. This is probably the case for light. We can say this. And if the perturbation is weak and we are in linear response, it means that for a given external perturbation, here Vx, we can get the change in density, in electron density, by using the density linear response function here called chi. And this is a pure material property. One can calculate it for the material once and forever, and then for any perturbation, you get the response. If you do this on the homogeneous electron gas, so this really homogeneous background system that we had before, when it's not symmetry broken, and you do it at the density of silver chloride, which is given by the Wigner-Seitz radius, 1.6, so it's a quite high density material, okay, you get this kind of picture. So what we here have is we put a perturbation in the origin, and then we look as a function of distance from the perturbation, how the density changes. We do this in different approximations, which are called RPA or adiabatic local density approximation. This is not important here. The important thing is to notice that we have a strong response and then we have oscillations. This is a static picture. So it's a static perturbation, no time, no frequency. And these oscillations is what you know from the Friedel oscillations in an electron gas. Okay? And it's like having a stone in water or something like that. Okay? But now the electron gas, of course, can respond dynamically. Okay? And this is a picture that you often see in textbooks. You have excitation energy versus momentum in the electron gas. In the momentum gas, you can, in the electron gas, you have a parabola and you can excite from under the Fermi level to above the Fermi level. And this gives you a particle hole continuum. You have a continuum of possible excitations in the gas. And then you have one sharp line here, which is a collective excitation of the gas. It's not taking one electron from a state below and putting it above. It's the whole gas in resonance, actually resonance of the electron gas. And it's called a plasmon. It's a very sharp line out of the continuum. And this energy at momentum zero is what we call the plasmon frequency. So you can ask yourself, what happens if you perturb your system now with an oscillating external potential at that frequency? And the result is given in the upper picture here. So down here we had the Friedel oscillations, which are actually quite weak and stopped at about 15 or 20 Bohr from the origin. So here we have what happens when we excite on the resonance, and you see you have a much stronger response. Note the change in scale, it's about the double. And then you have oscillations that go very far away, even at 40 Bohr, they have not stopped. So we have long-range oscillations in the resonance. And so we can ask ourselves, but what happens when we excite on an exciton frequency? What when we create the exciton? What happens in the material? And so we do this in time now, the linear response in time. And because we need the full linear response function, we actually need all the microscopic details. So usually people use the beta-salpeter equation. Yeah.
This is Matias Moreno. In your previous transference, why is it that you are getting an energy so close to twice the Bohr energy?
Excuse me?
In the previous transference,
yeah.
Why is it that you are having a 26 eV, which is almost twice the Bohr energy for the hydrogen atom? Do you understand that?
It's just because of the density of silver chloride. So we took the density of silver chloride, and this has a very high plasmon frequency. So, you know, if you take the classical formula for the plasmon energy, which is linked to the square of the density, you just get this number actually.
Okay, thank you.
Okay, so as I said, people usually calculate absorption spectra with the beta-salpeter equation, which we need for the excitons. But in an absorption spectrum, you just calculate a macroscopic average. So you calculate a macroscopic average of your response function. But now, if we want to look what happens, we have to get all the microscopic details. So we had to extend the beta-salpeter formalism to the microscopic response function. And this is what we did in 2019. This was mainly the work of Igor Reshetniak. And with this at hand, we could then see what happens when we hit an exciton resonance. And we did this in silver chloride in this photography project. And this was the thesis of Arnaud Laurin. So this is the absorption spectrum of silver chloride. You have the experiment in red and Arnaud's calculation in blue. And we will now look at what happens when we put an external perturbation that has a frequency in the band gap. If you do this, you hit the system with a frequency in the band gap, you have this kind of picture. You have silver atoms and chlorine atoms in green and black. And the induced density, you see a little blob here. Actually, almost nothing happens. The system is quite not interested in your perturbation, okay? But now we hit on the exciton resonance. And the result is this. So this is now a movie. I hope that you can see it. This is a movie in time. And you can see that we have a completely different color scheme here. You have a lot of things going on. And the most important thing is your perturbation was here in the middle, but the response gets far away over many, many unit cells. So this is actually a similar picture of what we had for the plasmon in the electron gas. This is now the real silver chloride, and we are not hitting a plasmon, we're hitting an exciton. And it's maybe the first time that you see what happens in real space when someone hits an exciton. So very strong response. And so you can see that our first principle calculations here allow us to go, as I said, beyond textbook physics. And you get a very strong and long-range density response on the excitons, which will be important, I guess, for many applications. And of course, we do this because we are interested in the physics, but also in the applications such as photovoltaics. Okay. Now, I don't know. I think my time is over, isn't it? Because
yes.
Yeah. So I will stop here. What I could have shown you also is what we do to design new density functionals and what we call an ecological use of models. But if you are ever interested in this, you can also ask me questions and we can talk about it, or you can send me emails, of course. I would then rather stop here and go to the last slide just to show you again the people, which I think important, and also our website, which is down here, and the codes we are using. And thank you for your attention.
Okay. Well, it's quite difficult to clap, but for sure, thank you so much for this very, very nice colloquium. And now is open for questions and comments. Please, I don't know who. Okay. Lucia, well, for example, in that last in your movie. No, you show for sure you have a very, very simple and small brilliant zone or crystal, no? But you said that the propagation of the exciton is quite large, and of course depends on this dielectric function or no for the screening. And in this case, for example, you're still having this small lattice constant for the calculations, or just in the self-energy is included that you are propagating more than
Okay.
one. I don't know if you are including another approximation.
I see the point, yeah. So
Yeah.
it's actually in two steps. First, we have to calculate the density response function, right?
Yes.
This is something you can calculate just in the unit cell.
Okay.
Because it's a matrix, so it depends. It's a function of frequency, it's a function of momentum in the first Brillouin zone, but it's a matrix in the reciprocal lattice vectors.
Okay.
So you have to calculate this whole matrix, and this was actually the new part with respect to what other people do in the beta salpeter world, because they only calculate the 0,0 component of this matrix, only the head, okay? So you calculate the full matrix. And once you have the full matrix, with this you can reconstruct the response in real space of any perturbation, but to show it, you have to go to many, many unit cells. This is why I showed you many, many unit cells.
Okay.
Because this response does not keep in one unit cell. It goes to
yes, that's what
was.
Yeah, and you have this kind of very phases and this kind of different quantum phenomena that you cannot ignore in some sense, no?
Yeah, there's a lot of things going on, actually. Yeah, it's very detailed.
Yes. Matias Moreno wants to...
Once again,
Okay, that's good.
I am a little surprised by your talk. Thank you very much. It was very motivating. But I am worried on how do you have control of different, let us say, inputs into your logic. You are in the last part of your talk talking about energies which are actually very, very large. And below that energy, I guess for a general material, you will have also excitations of phonons and every kind of beast, and also other correlations. How do you manage to say this is the important effect, and what is the logic behind that? I cannot follow that.
Okay, that's a very good question. Yeah, and maybe in my example of aluminum, you have already seen that it's much more complicated than what people usually say, right? So, of course, we have different scales. So, for example, the phonon energy scale is completely different from what we have in this insulators as electronic excitations. So we can certainly say that if we are interested in details on the absorption onset, for example, and suppose we have an indirect gap material and we are interested at the absorption onset, we cannot neglect the phonons, because if we are interested in the details of the absorption onset, we can get indirect transitions because we have coupling to phonons, right? So we can say that we don't care about details about of the absorption onset. We, for example, say we want to know where the first bright exciton sits. And then you have to say how important will be the phonons on the position and the shape of this first bright exciton. And then we have to admit that we have a precision that is not better than, let's say, 0.2 electron volts. Okay, we cannot say, I give you a milli-electron volt precision on this peak. Why? Because again, when we excite, we can couple to lattice vibration, and this can give us additional things. And by the way, phonons, we can consider phonons to be bosons, like plasmons are bosons. And so I showed you the satellites in the case of the bulk aluminum, which are due to electronic bosons, but you can also have the satellites due to the lattice vibration. And it gives you a series of satellites just on a completely different energy scale. So you are very, very right. I mean, there are many more things in a spectrum, and you have to be very careful and say, what am I interested in? And with which precision can I give the answer, right? And you cannot pretend that you are more precise than that, or that you can talk about things for which you didn't put ingredients. Absolutely. On the other hand, we cannot solve the full many-body problem in the sense that we cannot put the whole universe in the computer, right? And I think the role of theory is to simplify, because the role of theory cannot be to reproduce reality. If we reproduce reality, we will again not understand it. So we can explain trends. We can also be quantitative to a certain precision, but not better than that. I don't know whether you had a particular point where you thought that one should be more careful, or whether this answers.
Yeah.
No, it's okay, but I have not done that kind of calculation, and I wanted to learn what is the spirit and where your approximations are cutting some other effects. Thank you very much.
You're welcome. Thank you.
Okay. I don't know if someone else have a question. Arturo, please.
Thank you very much for this really nice talk. I have like a very technical question. Like in your Bethe-Salpeter equation, can you deal with frequency dependence also, in like the full?
You mean frequency-dependent electron-hole interaction?
Yes.
Okay, not in the things I have shown you, and it's very difficult. I don't know how familiar you are, but when you put frequency dependence in the Bethe-Salpeter equation, you have two problems. The first one is that the equation now depends on 3 frequencies, and you can integrate one out, but you still have a 2-frequency equation, which makes it much more complicated. And the second one is that when you put the frequency dependence in the electron-hole interaction, you also have to put it in the GG part. So you have to take fully dynamical Green's functions, because there are cancellations. This has been shown by Del Sole and Bechstedt and others. So this makes it enormously more complicated. And then there is a third point, which is, suppose you can do it, will the result be reliable? And here we have a very subtle point, because I have shown you the Dyson equation. The Dyson equation is an equation where you put a self-energy and then you invert the Dyson equation, and you get something that gives you a sort of series, right? You can expand the Dyson equation. So for example, if you put a self-energy to first order in W, your Green's function is not to first order in W, it's to infinite order in W, because you expand the Dyson equation. And this is a sort of inconsistency. And this inconsistency has good and bad points, and it's very good to give you quasi-particle energies. But it's not at all a good thing to give you satellites. And this is why I had to switch to the cumulant in the example of the satellites, okay? And so every time you have dynamical effects, this inconsistency strikes you. And therefore, I think that the good way to go, if you want dynamical effects, if you move to a frequency-dependent electron-hole interaction, is to also go beyond this Dyson equation, low-order Dyson equation approach, and to move to a cumulant formalism. And we did this, I think, 2 years ago with Pierluigi Cudazzo. So if you're interested, there's a paper by Pierluigi Cudazzo and myself, and we proposed a cumulant expression for the two-body Green's function. And this takes the frequency-dependent electron-hole interaction into account, and I think it's the most appropriate way to do this.
Okay.
Thank you very much.
Thank you.
Okay. You have another question or comment, Arturo? No.
No.
Okay. Okay. I think it's time for you because it's late for you, and you said it's lunch for us. But I really appreciate your talk. It was very, very nice and inspiring. And of course, I'm really happy to see you again and having you here, even virtually. And thank you so much. And I hope to meet you again in person. No?
Yeah, thank you, Cecilia. I was also very happy to see you again. And thank you, everyone.
Thank you.
And, don't hesitate to send me an email if you have further questions.
Yes. And if you don't have the email, I have the email. So don't worry about that. Thank you again, and see you soon.
And bon appetit.
Bon appetit. Bon mois. Okay.
Bye-bye.
Bye-bye.
Thank you.
Yeah.